Hello and welcome everyone to the 19th episode of Ask an Astronomer. We are here to ask all your questions you have about astronomy or science in general, about our life as researchers and anything else you want to ask. And I'm here today with Frugina. Do you want to introduce yourself and tell us a bit about what you're working on and kind of what's your research about?
Yeah, sure. Hi, thanks for having me here. I'm Frugina, and I'm a fourth year PhD student at the University of Cambridge. I'm a cosmologist, and I specialize in the evolution of the very early universe. So, how early are we talking? Well, strictly speaking, my work is all to do with the first 10 to the minus 32 seconds. So, this is when the universe is thought to have undergone an accelerated expanding phase called cosmic inflation. And this had some pretty important consequences. So, first of all, it is thought that all structure that we see today, so the galaxies and their clusters and the kind of empty space in between, started off as, or were seeded as quantum scale fluctuations during these primordial times. And so it is key to understand the origins of all structure. It is key to understand how these came about and how they were distributed. And so my work is partly on kind of the theory of what initial conditions these quantum fluctuations started off from, and also how they evolved. And I wrote some code on to solve a specific kind of equation that happens to be the equation that describes the evolution, the growth of these perturbations. And so while they started off being quantum scale, during inflation, this accelerated expansion, they were stretched to macroscopic scales. And we can actually model this. So if we can model this quickly, then we can actually kind of simulate from a split second after the Big Bang how these quantum fluctuations evolved, and then later on, there was something called recombination, which is when this kind of relic radiation was emitted that we can actually still see today, the cosmic microwave background, and these quantum fluctuations had an imprint on this cosmic microwave background. So you see that on the slide that was just brought up. This is basically the sky in the microwave domain, and the kind of variations of color show differences in the temperature of this radiation. And these small differences that we see, well, they are indeed very small. So there is kind of an average temperature of this, which is about 2.7 Kelvin, so minus 217 degrees Celsius. But the small kind of color differences show variations of the order of microkelvins. So basically, yeah, this shows that there were these quantum fluctuations and matter was not uniform in the early universe. And by looking at this and looking at the statistical properties of the cosmic microwave background, we can narrow down the kind of physical interactions, the physics of these quantum fluctuations. Yep.
Yeah. So basically, these really small kind of quantum effects of inflation became the hot and cold spots in the universe, and those hot and cold spots eventually kind of became, I guess, clusters of galaxy or like really large kind of structures.
Yeah.
How large were these fluctuations kind of during inflation time and like with the CMB? I mean, today they're kind of what we would call order one, right? There is matter or there's no matter. So they're like really large compared to what we usually see in cosmology. So the cosmic microwave background, those changes, like actually, I mean, this image just shows kind of red and blue spots, and they're like, I think what was it, like 1 part in 100,000 is like the change in temperature. So it's like,
so it's the actual temperature is of order 1 Kelvin, and then the fluctuations are order kind of tens of microkelvins or maybe 1 microkelvin, so 100,000th of a Kelvin. Yeah.
Okay. And yeah, right. So and during inflation, they were even smaller, right? Or were they the same size? Like, I don't know, a split second after the Big Bang, when you had those initial conditions, were those kind of hot and cold spots even weaker, or were they similarly strong as during the time of the CMB?
Oh, good point. They will have been weaker because basically what happened is to these initial fluctuations or cold and hot spots, they were also spots of increased density or decreased density, and this kind of density contrast between the two just gets exaggerated as time goes on due to gravitational collapse, so that the dense spots get even denser. So yeah, they were even smaller, but yeah, I wouldn't be able to tell you kind of what the exact density contrast was.
Okay.
Yeah.
I mean,
but I could do like a back of the envelope calculation for next time, maybe. Or
okay. Yeah. It's someone interested. We will do the calculation, but as long as we can stick to this. Also, I forgot to introduce what we're doing here. So, by the way, I'm Stefan. I didn't say it. We are both PhD students at Cambridge. And what you can do in the chat, in the YouTube chat, you can ask some questions. So you can just go on the YouTube link and send us questions in the chat. Or if you prefer and don't want to make a YouTube account, you can go on slido.com and enter these number codes, so 74747. And then, by the way, the link is also in the YouTube description. And then you get to slido.com and can just send us questions there without making an account. Otherwise, if you're watching from Facebook or Twitch or Periscope on Twitter, or Periscope, which belongs to Twitter, you can also ask questions in those chats. Just ask us anything. We just got one question in the YouTube chat, although I'm not sure what exactly the question is. So maybe you want to clarify. I'm happy to answer the question, but I'm not sure what the question is. So you talked about learning physics and GR.
If the question is more related to kind of academic life, then we're happy to answer questions about that as well.
Yeah.
Just a bit of a footnote to the kind of size of the fluctuations. So so they were about 1 part in 100,000, as we see in the cosmic microwave background. So that was emitted about 400,000 years after the Big Bang. And what we see today is, there's a huge contrast. We are here on Earth with our average density of 5.5 grams per cubic centimeter, and then right outside there is just space, and with a incredibly low density. So over about 10 billion years, it had time to evolve that much. So my guess would be that the density contrast during the time when the fluctuations were seeded were actually fairly similar to what they were in the CMB, just because of the kind of time difference.
It also depends on what kind of stuff is in the universe, right? Like if the universe is full of radiation, this really hot, the universe in the beginning was really, really hot. Even atoms couldn't form. It was super hot. And when you think about matter kind of falling together into clumps, it doesn't really work if everything's a burning fireball, as some people would say. It's not a burning fire, but it's really hot and dense, and it's hard to kind of form clumps of matter in that environment. They kind of to collapse into larger things.
It depends on what the kind of leading or most dominant physical interaction is that drives the kind of the general physics, and if the universe was a hot mess, then it was a kind of kinetic interactions and collisions that may have driven it. But kind of as we get closer to the Big Bang, there is less and less that we can say, because as the universe gets hotter, the kind of characteristic energy scales that were relevant also get higher and higher. And at some point, we reach a scale where we know that we cannot test these energy scales on Earth. Not even in particle accelerators. And we know that our kind of description of our theory of everything, standard model, quantum field theory, and so on, they kind of break down at some scale, or at least change, transform at some scale. So there's, as we get closer to Big Bang, there's just less and less we can say for certain.
Yeah. Okay, so there was one question I got actually a few weeks ago that I couldn't answer during the live stream. Which was so we talked in the live stream, we talked about black holes and how they form when you have kind of a high enough density of matter at some point, then this point can form a black hole. So, for example, when you have a star that collapses into itself and is large enough and dense enough, that it can form a black hole. And the question that actually a really good question was, that was asked on YouTube, was kind of in the beginning of the universe, like shortly after the Big Bang, everything was really, really dense. So did the universe kind of form a black hole at that point? Or like, well, what did happen there? And we actually had quite a long discussions in the last coffee break.
Yeah, that was a really good question. Yeah.
Do you want to say a bit about that?
Sure. Yeah, we can kind of talk through it. Together. But so to begin with, let's talk a little bit about why, or kind of the description of black holes and this description of spacetime. So kind of general relativity, if I had to summarize it in a nutshell, is that matter tells spacetime how to curve. Spacetime tells matter how to move. So the presence of matter kind of alters the geometry of spacetime. Much like if you had like a bed sheet that was stretched out, you dropped like a heavy ball on it, then it would like create an indent. So that would be kind of, this bed sheet would be spacetime, and then the ball would be mass or matter, and around the matter, at least locally, that kind of geometry of spacetime would change. And why that's significant is that kind of everything, every body, even light, follows trajectories of this spacetime called geodesics. So these trajectories are the ones that bodies follow when they are only acted on by gravity, without any kind of other external forces. And in the presence of matter, the geometry of spacetime changes, and so the kind of curves that bodies can follow when they are in free fall, so only acted on by gravity, also change. So that's the spacetime tells matter how to move bit. And black holes are an extreme case of this. So if there was just a black hole, just some mass in vacuum, completely isolated, then we actually have a pretty good description of the spacetime distortion that's caused by the black hole. And the geometry of the surrounding spacetime is described by something called the Schwarzschild Metric. And this just tells you kind of how physical distances are calculated on this curved spacetime. And the point about this metric is that it has a singularity. And so basically you can compute that if there was kind of spherically symmetric balls of matter, then what would the radius be that if you compressed matter to be within that radius, you'd get a black hole. So and that's called the Schwarzschild radius, comes from the Schwarzschild metric. Yeah, and so it's a good.
Yeah, what's actually really interesting about this kind of Schwarzschild metric is that I think it's one of the first, if not the first, kind of solution that people found to general relativity, actually. Mm-hmm. So when Einstein came up with general relativity and kind of wrote down the field equations in the kind of the papers, like he didn't have a solution for them. He just like, oh yeah, these are equations, but no idea how to solve them.
Yeah.
And then I think Schwarzschild was like one of the first people who looked at the equations, like came up with like, okay, in that case, like in this special case of you have like a spherical mass somewhere in the vacuum, you get the solution. And I think there was a bit of discussion actually about this, because Einstein didn't like the idea at all, but it was a valid solution. Yeah. And at some point we actually figured out, oh, this actually crazy looking solution really exists out there in the universe.
Yes. Yeah. And I think kind of an anecdote is that Schwarzschild was drafted, and he actually kind of worked on this solution while at war, which is the definition of badass, I think. But so do you want to talk about? There are actually very few scenarios for which we know how to solve these equations analytically. So do you want to talk about maybe the other well-known case of when we know the solution?
Yeah, I think so. The other kind of really well-known one is the so-called Friedmann, Lemaitre, Robertson, Walker metric, which is more or less simultaneously discovered by 4 people. And basically what it describes is when you have a universe which is the same everywhere, more or less. So it's all the matter is like nicely distributed throughout all the universe, with small, like really small, tiny changes at some places. And this seems like kind of useless solution, right? Because they say, yeah, well, not everywhere is the same. But if you look at the universe on large scales, and actually I have a nice picture for this here. This is a simulation of how the universe looks like if you zoom out enough. And it kind of looks the same everywhere. So you see at some places it's a bit more dense. At some places like it's more dense. There it's like a hole, a void, what we would call it. But mostly it's kind of the same everywhere. And that's
the cosmic microwave background is also a really good example for this, because the big thing about it is that these fluctuations that you see are tiny, so it's strikingly homogeneous, it's strikingly uniform.
Yeah.
So go.
Yeah, right. Right, and then this solution basically tells you how this universe evolves, and the kind of interesting feature is you get what we call a scale factor. So basically what it does is it lets the universe expand, or in theory also kind of collapse at all scales. Like basically wherever you would stand, it would look like the universe expanding around you. And this feature is, well, what we now know as the expansion of the universe, and we're very familiar with it. And basically it tells you when the universe expanded, how fast, and especially it tells you, for example, when you have something like inflation or something like dark energy, what we have today, that the universe grows exponentially. So something that's 1 meter today will be 2 meters on the next day, and 4 meters on the next day, etc., growing faster and faster. And this is kind of what drove inflation, this huge expansion. So basically this Friedmann, Lemaitre, Robertson, Walker metric is what you would use to kind of describe inflation, and you would get out these really, really, really fast growth of the universe.
Yeah, so basically, the early universe, in the case of the early universe, the Schwarzschild metric is not really something that you can use, you can apply, because it only describes matter in that is surrounded by vacuum, and we know that in the early universe that was not the case, or we think that was not the case.
True.
Yeah, but I guess interesting to mention that you can get down to small enough scales where you'd have kind of clumps of matter surrounded by approximately nothing. if you get to small enough scales, right? And so, I mean, these could be deemed black holes as well, and just tiny.
Actually, there's a theory about so-called primordial black holes. So that would be black holes that are created kind of in the beginning of the, like very, really, really early on in the universe, that just existed, like might even still exist today, and might even make up a part or maybe all of dark matter. That's a thing that people are actively looking for, although it's a very active topic of research, and people are not sure whether or not it could be dark matter. There's a lot of discussion about this. But yeah, maybe back to the question. So the question was basically, okay, I have this universe which is expanding really fast, but I also think I could have kind of a black hole, like if it's dense enough. And I mean, that wouldn't make sense, because the black hole, like nothing can go out of the black hole. So, and the black hole can't expand. So that those two things wouldn't be compatible. And if those would be applicable, you would have found kind of a hole in the theory. But of course, what you just mentioned, the Schwarzschild metric is really not that well applicable in that early universe. And you can actually think about this a bit kind of with a bit of intuition. So when you think about a black hole, basically what's happening is you have at the edge of a black hole lots of force pulling you into the black hole, all the matter inside, and it's really a lot of matter. And basically nothing on the outside pulling against you, so that then you fall in. And of course, this explanation is a bit of a kind of not exactly true, because with general relativity, everything is a bit more complicated than things pulling at each other, but it's basically the idea. And when you look at the early universe where everything is dense, there's just pulling in all directions. So it's not like you just have one point where the pull comes from, where you could have a black hole, but it's dense everywhere. So you get pulled in all directions, and you don't really get a black hole. You just get this expansion, this Friedmann, Lemaitre, Robertson, Walker behavior. Yeah. We did actually a live stream 2 weeks ago where we got tons of questions which we still didn't answer today. So maybe we'll take some of those questions while we are letting you time to write your questions. So go ahead, if you're watching, send us your questions in chat. We are ready to answer whatever you send at us, probably. One of the questions from last time was, what is the craziest thing that you have kind of come across? I think there are a lot of very crazy things. Do you want to start with a few nice examples?
Yeah, there are definitely a couple of mind-blowing things. Yeah, well, to me, it's pretty crazy that we have the cosmic microwave background as a source of data, and that's because, as I mentioned before, under the theory of inflation, that the kind of currently most widely accepted kind of standard model of cosmology. So this was, under that model, this was emitted 400,000 years after the Big Bang. And at that point, we were very far from having any stars or galaxies or anything like that. So, if we had a telescope that could look really far away and could detect really faint objects, even then, there would be a time, kind of a look back time or a distance at which there would just be kind of darkness, at least from stars. So we wouldn't observe starlight. And that's kind of how, at least in the optical, that's how far we can probe back in time. But because we have this cosmic microwave background, so this was light that was emitted 400,000 years after the Big Bang. Before the emission of this, matter and radiation kind of existed in equilibrium in a plasma state. So this was a kind of a hot soup where matter was ionized. So we didn't have neutral hydrogen. We just had kind of protons and electrons like flying separately. And in this plasma, light was essentially trapped. So light interacts with electrically charged things, but it doesn't interact with neutral things. So light kind of scattered off many kind of rogue electrons in this initial plasma, and so the universe was said to be opaque to radiation. But then, as the universe cooled and expanded, we started to have neutral hydrogen forming because the kinetic energy of electrons and protons wasn't kind of large enough to keep them apart. And so basically, as neutral hydrogen started to form, light no longer kind of interacted with the surrounding matter, and they ceased to be in equilibrium, and light could just kind of free stream, can travel in an unobstructed way. And it's still, as it gets to us, or as the cosmic microwave background got to us, it was kind of largely unchanged. And so we have this kind of pristine imprint of, or the pristine picture of what the universe looked like so close to the Big Bang, and that's insane. Yeah, that's number one thing, but I could go on. Do you want to say your favorite?
Yeah, actually, while you were talking about this kind of, that we get this picture of the Big Bang, actually we had like our professor told us a bit of a story about that. And when you look at it, this light that you see there in the Big Bang, not all of it comes from the Big Bang actually, but only about 95% come from actually from the kind of the time of like 400,000 years after the Big Bang. And the other 5% approximately come from very recent universe, so like the last few billion years. I think I agree that's a very broad definition of very recent, but it's definitely not from very early, but it's kind of late universe information. And the cool thing is about like us living today, like these at 14 billion years after the Big Bang, is we can see both things. Like we can see both the really old stuff and the new stuff, and that's kind of a really lucky kind of accident, you could almost say. Like if we had lived like far in the future, we would have no hope of ever seeing this picture of the Big Bang, but we would just see the new radiation that's coming kind of from the ions that were created by the stars. And if we had lived, well, much further, like much earlier, of course we would only have seen the early universe picture. Would still have been interesting, but of course I think now we have the best kind of both. Both words. I do think there was one second. There was a question in the chat whether or not why the sound is so low. Can you check if it's better now? I did switch microphones in the meantime because there was some crackling going on in my other one. So now we should be should be fine again. Let me know if it's still bad, or let me know if it's better now. Okay, go ahead. Sorry.
Oh, yeah, no worries. Yeah, another crazy fact about the cosmic microwave background is that, so because this is kind of ordinary radiation, what's another kind of consequence of the universe's expansion is that any radiation, so I'm going to be talking in terms of photons, so like the kind of particles or quanta associated with light, they lose energy, so their wavelength gets stretched with the expansion. So what we can see today is a radiation in the microwave domain, but there was a time when this radiation was in the optical part of the electromagnetic spectrum. So there was a time where, you know, if we were if there were humans, they would have seen the kind of an orange sky, or, you know, their optical radiation. Yeah.
Yeah, that's
Yeah.
really cool.
That's pretty cool.
Although I'm not sure if we had planets at that time, though.
Sorry?
Like, did we have planets at the time when the sky was still...
No. I'm pretty sure we didn't. Yeah.
But
yeah.
it's still cool, yeah. At some point, when I have a time machine, I will go back and look at the orange sky.
Just look at the orange sky, yeah. Yeah. Working on the kind of these quantum scale perturbations in the early universe, the kind of theory that we use to describe them is called quantum field theory, in which you know, fluids or matter is represented by fields. So these kind of functions that have a value at each point in space. And quantum field theory is a great theory. It can predict the kind of half-lives of particles and the probability or so-called scattering amplitude of some processes. But at the same time, it does yield some pretty inconsistent results as well. And so some of the biggest kind of unanswered questions in physics have to do with quantum field theory. And one of them, which is kind of my favorite, is how broken quantum field theory is when it comes to the vacuum. So one of the things that quantum field theory says is that there is no true absence of matter. Like, there is, even in vacuum, even at the lowest energies, there are processes which happen on short time scales where kind of particles get created and then destroyed. And there is, because these kind of fluctuations happen, there is an energy associated with vacuum. And this is like a 0-point energy. And you can use quantum field theory to predict this theoretically, and you can also measure it. And the difference between the prediction and the actual observation is 120 something orders of magnitude. So that many factors of 10.
Wow,
that's a pretty big discrepancy.
Yeah, something must be wrong there.
And it's crazy how quantum field theory can yield like such accurate predictions when it comes to kind of everyday energy scales, but at the same time like be so wrong when it comes to low energies.
Yeah. Like even when you look into like particle colliders, like the Large Hadron Collider and CERN, they hit particles at each other and like look with the best experiments we can build and look like at many digits after the kind of comma, what is the masses of the particle, the charges, like spins, all the things, and they all work out, well, almost all work out really, really well.
Yeah.
And then they have this thing that you try to calculate, you know, some cosmology and goes wrong horribly. But then there are things like you can use quantum field theory, I'm pretty sure, to kind of calculate how the early universe, like kind of seconds, I think it's seconds after the Big Bang, when you have like quarks and like the temperature transition in the early universe. So how hot it is, and then kind of quarks combine to protons and neutrons, and then the temperature changes slightly, and then they combine to like atomic nuclei, etc. And all this works out great. Like this you can just use quantum field theory. But then for this part, what we call actually the name of this phenomenon is called dark energy, like the thing that makes our universe expand, which should in theory be the vacuum energy from quantum field theory, but in practice just doesn't work out at all. Yeah. One of the crazy things on my side would be that what we just kind of like talked briefly about in the beginning, was this idea that everything we see today, like all the structure that we have, like the only reason there's not nothing in the universe is that there were like some quantum, like random fluctuations in the early universe that just got blown up by this inflation to be real, kind of, and that then suddenly just made, you know, hot spots, and that hot spots made galaxies, and now the galaxies made suns and planets, and we're here. That's super impressive. Like, it's just some random fluctuation that made
although, you know, so there is, we talk about inflation as if it was kind of certain to happen, but like it is, we should probably say that it is a hypothesis, right? And there is only indirect evidence that inflation happened. And just wanted to mention a couple of things, a couple of factors that kind of support inflation. And the first thing is that even though, you know, it seems like a crazy coincidence that quantum fluctuations were present at the right time and they got blown up to macroscopic scales and then created all of large-scale structures, it would be even crazier without inflation. And by that I mean, so one of the problems that we face, or cosmology faces, if inflation didn't happen, is why the cosmic microwave background is so homogeneous. So basically, if we project back what these fluctuations looked like back at the emission of the CMB, without inflation, the kind of spots on the sky that would have been in causal connection with each other, meaning that, you know, one point can actually affect the other point. So the physics at one point can affect the other, would have been actually quite small on the sky. I think about 0.5 degree or 1 degree. In comparison, that would be kind of the size of a full moon, I think. So a full moon on this kind of whole sky area. So they would have been actually quite small. And if these spots were causally, you know, not connected in a causal manner, then the fact that they appear to be the same temperature, that's pretty nuts. So that would have been a complete coincidence. The fact that, you know, because one would expect that if they are not in causal connection, if the physics at one point cannot affect the physics at the other point, they would just be kind of temperatures all over the place, and it would be made up of these kind of highly different or patches of highly different temperature of the kind of scale that I just said. And it isn't. And so this is it's a fine-tuning problem. And what's kind of very appealing about the theory of inflation is that it explains why the cosmic microwave background appears so homogeneous without having to resort to kind of, it was all a coincidence. That they started really cool. From the same temperature, these patches.
We just got a question in the YouTube chat about the very redshifted galaxies in Hubble's deep field image, and now I'm rummaging through my drawer to find the Hubble deep field image, which I might have in here. Here we go. A Hubble deep field image. So what this is basically what we did in the 90s. And we did take the Hubble Space Telescope and search for some, you know, boring dark patch of sky. Took the telescope, pointed it at that patch for 10 days straight, and just like, let's see what is there, right? You don't see anything there if you just look at it, so just point the telescope at it. And like after 10 days, they looked at this and like, you see thousands of galaxies. Like if you do a count, I think it's like 2,000 or 3,000-ish that you can see from this picture. And actually they're like, there are much more galaxies. So what they did afterwards is basically take a small section that's like kind of looks boring and black, point the telescope even longer and call it ultra deep field and find even more galaxies. So there are lots of galaxies basically in the sky. And what you notice is the further away the galaxy is, the more red it looks. That's an effect called redshift. So that's what you refer to in the question. And let me just explain this for everybody else as well. And basically, when the light from a faraway galaxy kind of gets sent out, it takes really long to get to us, like potentially billions of years. And over this time, the universe expands, And during this expansion, the wavelength of the light shifts. So when you have a, let's say, yellow light that has a quite short wavelength, and then your universe expands and the wavelength gets longer, you can get, for example, to a red light, so that has a longer wavelength. Yeah, right. Which is why it's called redshift. And basically this, yeah. So basically that's why in pictures of really far away galaxies, they all look more red. And now the question is about if those galaxies have developed the same way as the galaxies in our neighborhood. And I'm pretty sure that they did, but there's one big difference. So the galaxies you see there are much, much younger than our galaxies. So I'm not aware of what exactly the age is of the galaxies in this picture. I think they might be like, this picture might, so the distance to the galaxies, I think, is like a few billion years in like light travel distance. So we see the galaxies as they were a few billion years ago. So, and they did develop similarly to the galaxies in our neighborhood, just as it was here long ago. So basically what galaxies, what happened with kind of the, if you look at galaxy evolution kind of from really early on until today, there was some point, I'm not sure if I can get the time right, it's like a few billion years after the Big Bang, where the galaxies were very active, so lots of stars were formed. It's also called cosmic noon. And the later you get, like we kind of the more recent ones, the more recent galaxies don't form that many stars. It's still a lot of stars, but not that many anymore. So in a certain way, those galaxies were kind of a different kind of galaxies, like the old school galaxies, or we have now the newer ones. But otherwise, they form very similar.
Yeah. So what's nice about these oldest, most redshifted galaxies is, so they, as far as I know, they tend to be elliptical in shape. So the ones that are kind of more local or later time galaxies, they tend to have these beautiful like spiral arms, just like our galaxy. Yeah. But they can also be irregular in shape. But so these oldest galaxies tend to be elliptical. If you look at them through an actual like amateur telescope, you can have a look at some elliptical galaxies. They just look like very dense, like fuzzy clouds, with many stars, as Stefan said. And so yeah, they are described as red and dead. Their spectra is red, and they are no longer forming any stars. And what's cool is that, and again, probably another reason for inflation is that, so the age of this kind of oldest objects, these elliptical galaxies, they can be used to throw out some cosmological models, because basically if your cosmological model predicts that the universe is younger than these oldest objects, well, then it's probably not very good. Yeah, that doesn't make any sense, right?
Yeah.
So there were actually a couple of scenarios or cosmological models that failed because these oldest galaxies were actually older than the galaxy, the entire universe that they predicted.
Yeah. And actually, this thing about like galaxies also really like they're two really interesting effects. So the one like we just discussed, like, this is redshift. So like when you have a normal galaxy, like you could have a galaxy like the Milky Way, it's just far away, then it would look red if you have a really good telescope. Although you probably wouldn't see that with an amateur one. But then you could also have like a normal galaxy, like a today galaxy, like really close to us, that just happened to be a really old galaxy that kind of already got, like it was maybe spiral a few billion years ago, and today it's more like it turned into an elliptical galaxy and is what you just said, red and dead, and it also looks red. So that's like those are, I guess, the ones that you can see, from like a telescope, and those are like two effects that both make galaxies go red, but they are quite different in, I think, at least in effect. So you have the kind of the old galaxies that do look red, and far away galaxies that do look red because their light is just very old. Which is quite interesting.
Yeah. So there was this question about the Riemann curvature tensor. So it goes, the Riemann curvature tensor becomes non-zero in the gravitational waves, so energy is conserved there. Question.
Do you want to explain first what the Riemann curvature tensor is?
Yeah, so
and what gravitational waves are?
Yeah, it's a pretty dense question, right? So the Riemann curvature tensor is a mathematical quantity that appears in the Einstein equations, so the equations that basically describe how matter and space-time geometry interacts. A tensor is it's basically like a generalization of a matrix. It's let's
it's a
just
collection
say
of numbers. That's fine.
It's just a collection of numbers. So yes, it's this thing. It's non-zero, or it's non-zero whenever, as far as I know, if you have like matter. So if you have like a gravitational wave, it will probably not be zero. And so energy is conserved there. Okay, well, energy conservation, as far as I understand, has a completely different origin, right? So there was this pretty excellent mathematician lady called Emmy Noether, and she developed a theorem which is definitely my, like, hands down my favorite ever theorem. And she said that conservation laws, so conservation of energy and conservation of momentum or angular momentum, these can all be derived from symmetries in the associated theory. A symmetry is basically things staying invariant, things being unchanged under a transformation. So a symmetry would be if you had, if you had a shape like this, like this square, this would be symmetric under a transformation that mirrors one page to the other. Now, the symmetries that cause conservation laws and happen in real life are a bit more complicated. So a symmetry under kind of shifts in space, so spatial translations in kind of mathematical language, or the fact that if I kind of move 1 meter that way and kind of things move with me, physical laws wouldn't change, right? So spatial translation, we can say, is like a symmetry of the theory that describes, or the physics that is describing our kind of everyday lives.
So basically, the physical laws in my neighbor's room are the same as the physical laws here. Basically, that's a symmetry that we find and that we
exactly. Yeah. And so that symmetry, a consequence of that symmetry is momentum conservation. So spatial translation causes momentum conservation. A symmetry that's a symmetry under rotation causes the conservation of angular momentum, which kind of makes sense in an analogy with the spatial ones. And then a symmetry under time translations. So the fact that if a couple of seconds later, the laws of physics probably wouldn't change. Asterisk. There should be a footnote here. That causes the conservation of energy. So the fact that energy is conserved in the universe in general, as far as I'm aware, it's not to do with the Riemann curvature tensor. It's just to do with the symmetry of the theory that describes gravitational waves.
Yeah.
That being said, so the asterisk was referring to, okay, but are the laws of physics actually unchanged during time translations? And the answer is, well, not quite. So actually, the fact that the universe expands, and if you have a photon or light just free streaming in an expanding universe, its energy is just going somewhere. So it's basically, its wavelength is getting longer and longer. So its frequency is getting lower, which means its energy is diminishing. Well, that's a sign that actually time translation is not exactly a symmetry. So energy conservation doesn't really happen on these cosmic scales.
Yeah, like a question that I often get asked, like, where's all the energy going? Like, isn't energy conserved? And the simple answer is actually no, energy isn't conserved.
It's not conserved.
It depends a lot on what you call energy. Like, what you would call everyday energy is not conserved. But of course, you can kind of come up with like a description of energy that takes into account these effects, like that is valid kind of for cosmology, and then you get a conservation of that thing, which you could call energy, but usually shouldn't, because those are different things. So yeah.
So that's actually that should be under the kind of crazy things or hard to swallow pills of physics. Yeah.
And
Okay.
yeah, right. And about gravitational waves in particular, basically what they do is kind of move space around, right? So, when you have, let's say, the gravitational wave goes through your window, it makes the window go a bit broader and a bit shorter, and then it goes window make it go a bit higher, and it squishes and squashes the window around, but it doesn't change anything in that. Like, I mean, first of all, this effect is super tiny. You don't notice it at your window. You need like kilometer-long tubes of vacuum with lasers in them to find this. But even then, like, it doesn't do any work. That's what the physicists would tell you. Like, it doesn't. You can't get energy out of a gravitational wave, which is why it does it doesn't like lose. What does it? I don't think you can, right? Pretty sure you can't. And basically that's why like there's no that's the energy is still conserved, I think. Yeah, I'm not that sure about that.
As gravitational waves travel, there are very few ways they can lose energy. Yeah. So
okay.
if that's what the question was referring to, then yes.
Okay.
Yeah. So that's why we can detect them basically, like on Earth, because it's one of those signals that doesn't lose its strength while it's traveling these kind of vast cosmic scales. Not like kind of radio waves; they get attenuated and yeah.
Okay. We got another super interesting question from YouTube. Thank you for that question. Basically about someone falling into a black hole. Those are my favorite questions.
Nice.
From an outside observer, the one falling inside the black hole takes an infinite amount of coordinate times. Does that mean that the coordinate from the outside one, the black holes never grow? Oh, okay, that's a good. Okay, so let me kind of explain what the question is referring to. When you have a black hole, it doesn't only mess up time, it also messes up space. I mean, it just messes up space-time. And what happens, like some of the more simple effects of a black hole are when you're close to a black hole, time goes slower for you. So when you want to travel to the future, go park next to a black hole, wait half an hour, come back, and you will be a few hundred years in the future, depending on how close you get. One of the more curious implications of this is that when you would, like, to take a ball and throw it at a black hole, well, that's now difficult. So, okay, if you're in space, let's say you're an astronaut and you're falling into a black hole, you would just fall into the black hole. You wouldn't notice. You wouldn't even notice it if the black hole is large enough. You would just fall past the event horizon. You would notice at some point, oh, my voice
asterisk
doesn't. Okay, it doesn't work anymore.
I have something to say.
Yeah. And you're inside the black hole, and kind of time isn't that weird for you. But for someone looking from the outside, basically, it looks like you never reach kind of like you get closer and closer to the black hole. You never stop, but you also never get into the black hole.
Yes.
Now go ahead with your annotations.
Yeah. So from the outside, you would an observer would see this pretty amazing sight. So if Stefan was falling towards a black hole and I was here on Earth and had a telescope and would see him, I would see an image of him kind of getting closer and closer to the so-called event horizon of the black hole, and he would kind of slow down and approach it kind of infinitely slowly. And at the same time, the light that's coming from him would be shifting, would be redshifting. So I would need to kind of update my telescope to be sensitive towards kind of the longer wavelengths, lower frequencies in order to see him. But in theory, I could kind of see him forever. For him, though, the question would be different. So he would, depending on what type of black hole he decided to dive into, he would experience different things. Counterintuitively, it would be more comfortable for him if he chose a supermassive black hole, so one that has kind of like 1 million solar masses, than a small one. And the reason is to do with tidal forces when you get closer to the black hole. So basically, the kind of gravitational force exerted on the edges of your body, if they are different, then you get a tidal pull. So same thing that the kind of moon does to us. And for a larger black hole, this actually, the difference between the forces on the two edges of your body isn't too big. So it wouldn't be uncomfortable to fall through the event horizon. Whereas for a small black hole, you would experience something called spaghettification, which is basically that the difference between forces on your toes and your head would be so great that you'd just be pulled apart.
I mean, you can imagine this on Earth. Like when you're standing on Earth, like, you know, the right way up, your feet are getting pulled towards Earth stronger than your head. So, I mean, it doesn't really do a lot on Earth because you're standing somewhere. But if Earth would be a black hole and you would be falling, your feet would be falling faster than your head, and you would kind of slowly get stretched out, or as you say, spaghettified.
Yes.
Yeah.
Yeah. So that's interesting, and it's a somewhat of a counterintuitive result.
So now the question: does a black hole never gain mass? So the idea is like when you say, when I never fall into a black hole, then I never the black hole gains mass when I fall into it. That would be my intuitive idea, right? So I fall into the black hole is 1 Stefan heavier and, you know, grows a bit, etc. But if I never fall into it, like never reach the event horizon, how does that work? Do I still does the kind of black hole still grow? Oh, I think it might be related to like the black hole actually growing. Like, so when, let's say you're like really, I mean, basically the idea is you're not just stopping kind of somewhat close to the black hole, but you're stopping really close to the event horizon. So
yeah,
and when the event horizon then grows, kind of it takes like it. Well, I don't want to eat you up, but it might just like be kind of that kind of mechanism that you just become part of the black hole at some point.
Yeah. So as you know, as the mass of the black hole changes, so does the kind of the radius of the event horizon, and the kind of like, obviously it wouldn't be a symmetric process. So the whole, yeah, you know, the event horizon probably wouldn't just be described by a radius. It probably wouldn't be circular. But that sounds like a challenge for like numerical relativity simulations. Yeah.
Okay, I might ask someone about this in the next coffee break, and maybe next week you will get a 10-minute explanation about that question.
Yeah. Well, what we can say is that, you know, from the outside we don't really observe black holes like that. We observe black holes that are active, so they are actively accreting on material or kind of sucking in material. And the material gets heated to really high temperatures, such that their kind of thermal radiation is in the X-ray part of the electromagnetic spectrum. And there are not a whole lot of things in the universe that emit X-rays, apart from black holes and the accretion disks of black holes. And if you look at an accreting black hole, then kind of the luminosity of this X-ray radiation actually varies in time. And this is because, well, the material that they are accreting on isn't coming as kind of uniform packets. It's coming as, you know, bits of larger mass and then bits of smaller mass and so on. And so the energy output is different. And so, you know, we don't see black holes as these constant things, although this is like an indirect observation of black hole, rather than a direct one. But yeah, theoretically, it's a good question. My intuition would be that we do observe the black hole as growing, but I need to like properly calculate this. So let me get back to you on that.
Okay, you also asked another question, so thanks for the question. The Lagrangian in general relativity depends on the metric chosen. So what happens at the event horizon and singularity?
Oh.
Yeah, so I'm not that sure about the Lagrangian in general relativity. Do you know more about how that looks like?
Yeah, so the Lagrangian has a really nice and simple
form. Or maybe
form.
what Lagrangian is, let's start with that one for the remaining part of the audience as well.
Okay, okay. So, right, the Lagrangian is a quantity that very simply, a quantity that describes like a mechanical system or physical system. In simple mechanics, it would be the kinetic energy of the system minus the potential energy of the system, but not kind of expressed in units of energy. Like it's not actually just a number, but it's expressed in terms of the coordinates that describe the constituents of the system. So if you had like a pendulum, then the Lagrangian would be some function of the mass of the pendulum and like the position at which the mass on the pendulum is during its swing. And in general, yeah, it would include like time. It would include some sort of generalized positions, and it would include velocity or generalized velocity of the things in the system. And what this Lagrangian is useful for is that you can derive the evolution of the system from this quantity only. So without resorting to thinking about forces and resolving the forces and where they act and what direction they act, you can actually get an equation of motion or like an evolution of the system purely from this Lagrangian. The catch is that this Lagrangian is actually fairly difficult to construct. It is all right for mechanical systems, but in general, for a general physical system, you have to take into consideration like what symmetries you expect the system to obey, and then you can write the Lagrangian based on that. So so in general relativity, if you have like bodies, then there is a Lagrangian that describes the motion of that system under general relativity, and it actually has a very, very simple form, and it does involve the metric. So it's basically just the length of a velocity vector, and the length, because the metric is like this quantity that tells you like how physical lengths work. It is involved in this, or it's included in this Lagrangian. So what happens at the event horizon and the singularity? Right. So the metric is a metric, or like the geometry of space-time is also a function of coordinates. It's a function of what the metric distribution is at that point and in this kind of surrounding points. At the singularity, well, the metric is singular. So basically it blows up, it goes into infinity, and so your Lagrangian is ill-defined.
So singular is the physicist word for dividing by zero, I suppose.
Yes. So, yeah, basically. So in the metric, you'll have a quantity that's like something over zero.
Okay, that
so
doesn't work well.
That becomes pretty ill-defined in the singularity, and so does the Lagrangian. So basically, what that tells you is that, well, you can't use the Lagrangian anymore, or the Lagrangian formalism of mechanics to describe the dynamics of the system at that singularity. Unfortunate. And the issue is that we cannot observe this either, because no information can leave the black hole. So yeah, unfortunately, I cannot answer this question beyond what I already said. And what happens at the event horizon? So yeah, the Lagrangian is well defined at the event horizon. So it just you just evaluate it at the event horizon, and at the event horizon something interesting happens to kind of the role fulfilled by space, the spatial part of the metric and the temporal part of the metric. So around the event horizon you would expect a difference in, therefore you would expect a difference in the Lagrangian and the difference of how the dynamics of the system works. But beyond that, yeah, it just acts like a normal Lagrangian, and you can still use it to kind of tell you the trajectory of an object.
Okay, yeah. So isn't that like, I guess it depends on how you formulate, or which kind of metric you use, because right? I mean, isn't there like in the Schwarzschild metric like some kind of dividing by zero at the event horizon as well? Like I think there's like 1/1 r minus Schwarzschild radius or so term in there. But I think there's like a good like you can switch the coordinate system to something that actually works in that case.
Exactly. So I was going to say that there are some singularities which are kind of natural. like that, basically that don't go away if you choose a better set of coordinate system. And then there are coordinate singularities, which are kind of artificial, and because you chose a bad coordinate system, and they are not that uncommon. So for example, if you wanted to use so-called spherical coordinates, there are points, kind of ill-defined points in a spherical coordinate system as well, like the poles. Yeah. So the issue with the poles is, what angle do you describe it with? There are
like,
three kind
to
of
give a practical example, if you're on the Earth and you're like on the North Pole, I forgot the word. Is it latitude or longitude? I think it's like what. Well, one of them is like doesn't make sense at the North and South Pole.
The longitude doesn't make sense.
Okay.
The longitude doesn't make sense because the longitude lines cross at the pole. Or
yeah,
you could also ask, like, where does your compass point on the pole? Well, it points downwards, but it cannot, right? So you would if you kind of run around the pole, you would expect it to spin, and that's basically it's not a coordinate singularity, but it is another kind of, it's an artifact that you get because your coordinate system is not well suited for the problem.
Yeah.
Yeah.
Okay, great. That's already 1 hour today. So thank you all for sending the questions. Thank you, Rina, for answering all the questions and being here. Yeah. We will be back next week again at this channel, this YouTube channel, Monday 6 p.m. So if you want to learn more, come back next week. And until then, see you and have a nice day.
Yep.